And this is a bit interesting problem. A point charge Q is located between two large parallel conducting plates A and B. The plates names are A and B. The distances from the charge to the plates are equal to L1 and L2. I can see that. The plates are connected by wire, conducting wire, it must be conducting wire, and determine the charges Q1 and Q2 induced on the surface of each of the plates. Look, there is a problem because field between the plates is non-uniform. So it is difficult to look for the distribution of charges across the plates. However, the total charge induced on the surface of plate will remain unchanged when the charge Q moves in its plane P. P is perhaps its plane parallel to the plates. So only the distribution of charge of the induced charges on the plates will change, and not the total charge. That is important to know here. No. And if you want to know only the total charge induced on the surfaces of plates and not its distribution, you can spread the total charge Q over the plate P. This is the plate P with certain total surface charge density as sigma. And this will not change the amount of induced charges and their charge distribution, and I think then the problem will reduce to the problem of uniform fields between the parallel plates. So I guess I'm going to think like that. The electric field lines begin at charge Q and end on the inner surfaces of the plates, so that if charges here and here are Q1 and Q2, so this I can immediately write that Q1 plus Q2 is equal to minus Q, because it's simple, because Q is spread on the both sides of the plane Q, and it can induce the side of it will have charge Q. This side of plate P will have charge Q1 and this side will have charge Q2. So these are basically negative charges. So minus Q1 minus Q2 is equal to Q, and that I can write simply here. If I write them not with minus sign, I can write them like there are charges Q1 and Q2 on these surfaces. So I can simply write Q1 plus Q2 is equal to minus Q, and immediately you can also write that sigma 1 plus sigma 2 is equal to minus sigma. Here sigma 1 and sigma 2 are surface charge density of the inner surfaces of the plates, and the field strength in the gaps between the plates are determined only by the charge densities of the surfaces between the gaps, limiting the gaps. So they must be something. I can write an electric field here as E1 and here as E2. Then we can write simply as E1 equals sigma 1 by epsilon naught and E2 equals sigma 2 by epsilon naught. And since the plates are connected, so I have formulated a problem perhaps. Since the plates are connected, the potential difference between them is 0. They are at same potential. That means E1 L1 will be equal to E2L2. This is the potential difference between the plates, between this plane P and A, and then plane P and B. And I can write this relationship as E1L1 equal to E2L2, and that means E1 is equal to pi 1, sigma 1 by epsilon naught, and E2 is sigma 2 by epsilon naught. So I can write one thing more here, that sigma 1 L1 is equal to sigma 2 L2 from here. And since sigma 1 plus sigma 2 is equal to minus sigma, so using both these relation, we can obtain the relation for sigma 1 and sigma 2 in terms of sigma and L1, L2. And I got here sigma 1 is minus sigma L2 divided by L1 plus L2, and sigma 2 you will get is minus sigma L1 divided by L1 plus L2, and that solves our problems. Because this relation is also valid for charges, you can write here Q1 equal to minus Q L2 by L1 plus L2, and Q2 as minus Q L1 upon L1 plus L2. And that's all. You have solved this problem. Thank you very much for watching. I'm giving them a stop, though these problems can be solved, but there are many more things still needs to be solved in the chapter of electrostatics. So I focused on potentials, charge distributions, and electric flux. They focus on in IIT JEE, but I have not taken yet the problems of Olympiads, and I will take them soon.